In the rolling hills of Moscow, Idaho, University of Idaho is a hub of innovation, opportunity, and community. It's where education blends with cutting-edge research, and students push boundaries in every field, from science to the arts, from entrepreneurship to technology. Join us as we explore the stories that make this university a powerhouse of not just education, but impact. Whether it's the bright minds in the classroom, the trailblazers in the field, or the leaders shaping tomorrow, University of Idaho is leading the way. In this half-hour special, we'll discover how U of I is making a massive impact from the heart of Idaho's Palouse. University of Idaho has received the prestigious Carnegie R1 status, making it the first university in the Gem State to join the nation's elite group of top research institutions. With only 187 universities nationwide with this classification, this achievement is major. U of I's Vice President Christopher Nomura walks us through what the Carnegie R1 status means to U of I and beyond. University of Idaho recently achieved Carnegie R1 status. That is absolutely fantastic. I know this is a very prestigious classification that marks the highest level of research activity in the nation. What does this mean for the university, and how did you reach this milestone?
You know, there are approximately 4,000 higher education institutions in the United States. And the Carnegie organization classifies all these different institutions. And one of the classifications that they use is for research activities. R1 is a classification for the highest, very high research activity. It's the highest research activity classification. Of those 4,000 institutions, only 187 of those have achieved R1 classification.
Wow.
And the benefits of being an R1 institution are manifold. That in itself is a huge attractant for top talent faculty, top talent students, and also industry partners. They know that they can rely on a university that can do research at the highest level. And importantly, we're the first in Idaho to achieve this classification. We're very proud of this, and we think we're contributing a lot from our research in this activity space.
And Chris, if people want to be involved in this high-level research, either as a student, as a professional, or maybe they're just curious and they want to know more about the innovation coming out of the University of Idaho, where do they go? What do they do?
Well, go to the website shown here on the screen, and you'll find out a whole heck of a lot more about all the cool research activities that are going on at the University of Idaho.
And among that research, and at the forefront of innovation, University of Idaho's Assistive Robotics Lab is transforming stroke recovery. Students aren't just advancing their fields, they're making bold strides to enhance the quality of life for others. Joel, Chris, thank you so much for having us in this incredible space. We're here at the University of Idaho Assistive Robotics Laboratory. And what's even more incredible is the work that you guys are doing to help stroke survivors in their recovery. So tell us about that.
Yeah, we are designing and building exoskeletons, and we're focused on creating technologies that are going to allow us to understand function and impairment better, and also to help us rehabilitate people better, learning how the process can improve function and outcome at home.
Okay, and then with that, though, your robots that you're building here, this is just one of a few things that you've been working on. You're using what we already know about the human brain to help stroke survivors with mobility and movement. Explain that. How can these robots do that?
In the first 3 months after a stroke, there's a kind of a new window that opens up in the brain that is kind of like when you were a child learning how to do things for the first time. Your brain is more plastic and able to relearn and grow neurons in a different way that is going to taper off. You can still improve later on, but it takes longer to see those gains. The more you train, the better. You get better outcomes by doing more work. And so early on doing a lot of therapy, and that's where robotics can take advantage of lots of time-intensive, repeated movements that they could do 1,000 times that would take forever to do in a therapeutic setting. And then the last one is active participation. So if the subject isn't actively involved, if this robot did all of the work, the subject wouldn't learn nearly as much as if they're actually trying. So we have to have intelligence in the robots that can measure the movements that they're doing and only assist as much as needed so that they can recover the most.
And what type of movements are we seeing in these robots? What are they helping people recover and be able to do?
So here we work mostly with upper limb devices. So Blue Sabino, we've got reach tasks that we can do. I can work on learning, like training somebody how to they use their arm to like grab a glass of water and drink something, or like grab food and bring it to their mouth and eat. Anything that you would do with your hands in your daily life, because you use your hands and your arms for pretty much everything. We kind of don't think about how much we just take for granted everything that we can do.
Well, in addition to our clinical robotics, we're also working on home-based devices that would be lightweight, wearable, non-powered devices, so things that you could just mount to your body and help give you some assistance back. Stroke patients often suffer from something called abnormal muscle synergies. What that basically means is when you try to lift your arm against gravity, often your biceps will contract and you'll be stuck with your arm close to your body. And so just by offloading some of the weight of the arm, a certain amount of stroke subjects have the ability to reach a much larger area with their hand. So if we can provide them with the assistance that they need, that they use in therapy to do practice with a device that can be just body mounted, then the hope is that they can reach more with their hand. We also make devices where we provide assistance to the fingers to help open the hand. And if you can open the hand to interact with daily objects, then the thought is for those projects to help people train in daily activities doing what they would ordinarily do and get way more therapeutic time to try to increase their chance for recovery.
What's the role that University of Idaho students play, though, in the creation of these robots?
We've had students that are involved in the design process, the build, giving feedback in here with subjects, participants that have had stroke. And Chris has a unique perspective on this.
And, been really fun to kind of get in from like just kind of an undergrad perspective of just kind of getting acquainted with robotics and the whole field, and then decided, well, hey, I can actually do a PhD. That's something that some undergraduate me wouldn't have even thought it was a possibility at the time. And I just really enjoyed the whole time here, getting to interact with our students and mentor them too as I kind of learned more and more. And yeah, now I'm in this faculty position, getting to teach people, mentor people, and really enjoy it. So it's a big motivator for anybody that kind of works on this stuff, for wanting to be able to do something that gives back and improves the world.
In addition to human health, University of Idaho is tackling global health as well, taking on e-waste. In 2022, over 62 million tons of discarded electronics were generated, making e-waste the fastest growing solid waste stream. Now a team of U of I researchers is turning this waste into opportunity.
I consider e-waste a variety of different materials, from consumer electronics to printers, cell phones, laptops, desktop computers, things that we use and then need to dispose of.
Whenever there's a new phone coming out or a new item coming out, people want to turn in their old phone and get their new phone. And so that's one of the reasons it's driving a lot of e-waste. I mean, new computer or an old computer, right?
Mm-hmm.
Where do they end up?
So how do we recycle e-waste? Because there's a lot of it, right?
There are some current methods that are being used, right? So most likely it's gets scrapped, and then gets shredded, and then from getting shredded it goes through some type of either a pyrometallurgy where it gets combusted or heated, and they burn a lot of things away, and they can congeal a lot of the metals. You can add a lot of like strong oxidizing agents and strong mineral acids, and that can just kind of eat the metals away.
I think one of the challenges that's associated with the current treatment methods is they are extremely energy intensive on the pyro processes, because you have to heat and melt everything, or hydrometallurgical processes, which typically use materials that are kind of one and done throwaway or are toxic and hazardous for the environment.
Tell me about the collaboration between your two departments, though, and how you're approaching the recycling of e-waste.
I'm the chemist and he's the chemical engineer, right? So I'm the one that we will make a compound, and he's the engineer, so he makes the process work.
The compound that we have can eat metals. So,
Eat metals.
yeah, as far as like dissolve them without being under harsh conditions. That's a benefit of our process. Not using water or very little water if you do use it. You're moving away from the hazards and the energy intensiveness of just recycling, but you're also not then mining it out of the ground, causing additional impacts.
There's a limited amount of resources in the world, and so it's so much nicer in my mind to go mine a landfill than mine a mountain or in the ground. And the metals we're talking about are copper, palladium, platinum, gold, nickel, cobalt now, as well as I guess there's a variety of rare earths as well that are quite valuable. So, and if you can separate them and recover them in high purity, then you have a wonderful product to give back.
So how does the process work?
So you start here with your waste. E-waste, your electronic scraps, right? So here's your circuit boards, and then we start breaking them up, and we put them into a grinder or shredder, and we get to these types of materials, right? So it's kind of coarse. Then we can keep grinding even further into getting some of the millings into some of these processes where they're finer chipped, right? And so from there, right now we're ready to introduce our compounds. Once you put the metal inside, it starts complexing and doing its magic that it can then turns into these other different materials. We can monitor this visually with a spectroscope, and we can monitor a lot of the things happening, on a variety of scales. And then from there, we take this to an electrochemical setup, and we don't have the electrochemical setup right here, right now in this room, but that's where we go to recover the metals at the end of the day. So
and regenerate the ligand too.
Oh, so then you take the liquid and then you purify it, I guess?
we use it again.
And use it again.
Just got funded by the National Science Foundation to keep pursuing this and to try to separate the metals and actually separate the metals individually. And because right now we can do a lot of these things with distinct metals, but can we do these things in mixed metal systems, and how good or how pure is it at the end of the day? And we want to eventually get this to commercialization, right? That's where we'd like to be in the next 3 to 5 years. Yeah.
From cutting-edge technology to exploring what's beneath the surface, U of I is taking innovation beyond the lab and into the field, literally getting their hands dirty. We'll explain next. Today we are celebrating U of I's R1 classification, elevating it as a leading research institution. We know a lot about the soil beneath our feet, but what about 9 feet below? At University of Idaho, groundbreaking research is uncovering secrets that could reshape the future of agriculture and the health of our planet. Michael, Zach, we are here to talk about those. What are those?
The deep soil ecotron, or an ecotron in general, is just the most highly instrumented kind of facility that is out there. So you have synchrotrons, rhizotrons, you have many types of facilities dedicated toward a discipline. This will be the only one dedicated to deep soil.
I mean, fully controllable, we have the ability to manipulate temperature, light, precipitation, all those sorts of things.
So you get to create the climate.
Yeah, exactly.
Soil is incredibly important. When we talk about soil, I think people typically think of topsoil. Mm-hmm. But why deep soil? What's the importance and the value of understanding deep soil?
Honestly, it's a large unknown, a big unknown. Zach and I always talk about it as kind of like our deep ocean, right?
Oh,
so we know a lot about the surface ocean, but we don't know a lot that goes on below that. And the same for soil. How does this surface, these things that we do on the surface of the soil, impact those deeper layers? And in turn, how do those deeper layers impact surface soils as well? That's a huge piece of this. We're also able to monitor a whole lot of different aspects of these soils, which is really difficult to do in the field. So you have to dig a pit in the field. It's a lot of work. When you do that, you're automatically exposing that soil to the atmosphere, to the surrounding environment. And so what you're studying isn't this intact contained system anymore. Yeah. And so we're able to do that here and continuously monitor that over a long course of time.
What could deep soil tell us about Idaho?
This is kind of replicating a study that we have going on in the field,
Okay.
where we're looking at like diverse cover crop mixes and a less diverse cover crop mixes. So cover crops have become something I think that in Idaho we're focused on, or beginning to focus on quite a bit. But again, like we're oftentimes only looking at the surface of those. And so here, you know, like at least here, we can already examine them up to 1 meter deep. It really accelerates the pace of research because we aren't beholden to the elements like you just mentioned.
Yeah.
So we can run these experiments to better understand how like agricultural practice might impact soils, surface soils and deep soils. So this is really just a temporary setup here until we're able to move this into its permanent location. And what we're actually going to have is really the soil depth that we'll have is really 3 of these stacked on top of each other. So the surface of the soil will actually be housed in this unit up here, where we're able to control the atmosphere, light, precipitation, all of those sorts of factors. And actually, this is just a temporary section. So there's an entire renovation going on a couple of doors over where these units will be housed.
Now, I understand that there are other ecotrons in existence. However, what you're doing here is basically the first of its kind.
It is totally unique from the get-go, from the people involved to engineering these and just designing them. They can do so many things that other facilities cannot.
What is your overall goal or future for this project?
Just gaining a better understanding of deep soils. It is a huge uncertainty. It impacts our ability to do research. It impacts our ability to do applied research and make recommendations to, say, growers. It also impacts our ability to understand how these soils are going to respond to future change. That's something that I think is a big piece of this, a big component of it. And that's, ultimately one of those goals is to just better understand how these soils play a role in, Earth systems.
Not just for Idaho, it's really for the entire nation and even the world. Because it's such a unique facility, we really want researchers from, all over the world to come here and ask their questions. And we have the personnel, we have scientists that can help with those research endeavors.
The University of Idaho is Idaho's land-grant institution. And as such, our activities are really focused at helping stakeholders across the entire state of Idaho. In particular, one area of great importance is in agricultural research. Potatoes are obviously a big deal for the state of Idaho. And if we look at what we need to do in order to have healthy potatoes, it's actually quite a complex process. They all start in a seed germplasm facility up in Moscow, Idaho, actually. Potatoes are very sensitive to all sorts of different pathogens, nematodes, like different pests, and so forth. And so that facility is state-of-the-art in the fact that it can keep things disease-free.
University of Idaho is not only focusing on agriculture, but aquaculture. From Idaho's most famous resource, potatoes, to a lesser-known one, burbot. A once endangered fish species in Idaho is making a major comeback that could impact not only the food supply here in Idaho, but possibly the country. Luke, Megan, where are we?
This is the Aquaculture Research Institute.
Okay, and you guys are studying burbot. What is burbot?
So burbot is the only freshwater cod. It has a distribution in northern North America, Asia, and Europe. And specifically in Idaho, it's in the Kootenai River.
And why are you guys studying burbot specifically?
So in the last 50 years, this fish has declined in the wild. At one point to less than 50 individuals in the state.
Wow.
There is a potential for this fish as a commercial aquaculture species.
Okay, so this fish itself could actually then help Idaho's economy. And does this fish in particular have a significance to any of the local tribes?
Yeah, it was an important food fish for the Kootenai tribe in particular. And so they're very interested in bringing this fish back in the wild. It's a white-fleshed fillet that is highly desirable by anglers and consumers alike.
All right, and I understand then the potential for this to be farmed, right?
Yes, so the University of Idaho has been working with this fish to figure out how to grow it in a hatchery setting, because this was the established way to bring it back in the wild, was figuring out how to breed it how to grow the larvae and then the resulting young fish, and then to release them. And so through that work, the university and the Kootenai Tribe of North Idaho has learned how to grow this fish through its entire life cycle.
Let's talk about how the burbot actually ended up being a fish that started dwindling in our waterways.
Yeah, so in the 1970s, Libby Dam was installed in Montana. And this changed the temperature and the flows of the Kootenai River. And this led to the burbot eggs not surviving as well as they could have, and then any larvae that did hatch out of the eggs, they didn't really have as many nutrients and places to live as they had in the past. And so this led to a sharp decline in the burbot population. And in 1990s, the burbot fishery was closed in Idaho. So it was actually closed for around 30 years. And because of the work here at the university, we were able to reopen.
What work are you doing here specifically that relates to that?
So specifically right now, we're looking at heavy metals. And so we've got an experiment where we're looking at burbot that came from waters in the Kootenai River that have high amounts of heavy metals. And we're looking at is their survival any different from the fish that we have here that aren't exposed to those heavy metals.
Because burbot are pretty resistant to most of the pathogens that affect like salmonids that we're more used to being on the commercial market, there are still some bacteria that affect burbot pretty harshly. So part of my project has been developing a vaccine against Eromonas. We've had pretty good success with that, and hopefully it can give a head start to these facilities that are starting to make burbot available on the market soon. I had never heard of burbot before, and I just think it's really cool how I'm getting to work on a fish that needs both commercial and conservation help, essentially. Being able to do both types of impact is really cool to me.
Welcome back to this half-hour special celebrating Idaho's first Carnegie R1 Research Institute, University of Idaho. With the rapid rise of AI and 3D printing, University of Idaho is already leading the way to make a positive impact around the globe.
Something that University of Idaho researchers are doing is they are developing specific artificial intelligence algorithms or programs that are helping us to analyze, for example, defects in nuclear fuel materials. And this is really important for the safety of the nuclear power industry. We're working on experiments to take waste lumber material that's going to basically be used in a 3D printing technology to build out these logs that can be used to build affordable housing.
Affordable housing is just one major obstacle our state faces that U of I is working hard to find solutions for, in addition to a natural challenge that plagues our state each summer season, wildfires.
So what is pyroerobiology?
So pyroerobiology is really exactly what the words sound like.
Okay.
And what we're doing is looking at the intersection of fire, things that we find in the air, so aerosols, and biology. So what it really is an intersection of the way that microbes, including things like fungi and bacteria, are aerosolized in wildland fire smoke, and understanding the biology of that and what it means for human life and what it means for ecosystems.
Oh my goodness, okay, and this is something that you actually discovered, or you created the term, right?
Yeah, we needed a way to talk about it, so we came up with a term. We realized a few years ago that this was a phenomenon that had not been explored. So is it possible that fires are producing microbes when they produce smoke? And do these microbes actually survive the combustion processes that they go through and make it into the smoke plume long enough to be transported to other places?
Okay, so then within these smoke plumes, what type of organisms do you find?
So we find a wide variety of different types of organisms. So we have, at this point in time, been able to identify using DNA analysis about 3,000 to 5,000 different bacteria.
Oh my goodness.
And many hundreds of fungi. And it is common for a lot of organisms to be in the air at all times. So any day that you're breathing air, you're also breathing in some microorganisms. but the concentrations and the diversity that we find in smoke is much, much higher than what we find in ambient air conditions. The kind of microorganisms that are on the surfaces of plants, things that get kind of picked up by the wind, those are in ambient conditions. But what we find in smoke from wildfires is that soils also get mixed up because there's a lot of wind that's created by the convective winds of a wildfire. And the organisms that are inside plants also get exposed to aerosolization because the plants are being broken down during the combustion process. So we get a lot more organisms, different types of organisms, and some of those organisms might have consequences for downwind.
Why is pyroerobiology so important when it comes to wildfires and the impact of smoke?
With that higher concentration of organisms in comparison to ambient air characteristics, what that suggests to us is that people are breathing in a lot more than they would be in normal times when there's smoke in the air. And we of course know that smoke in general has some significant health consequences, especially for people who are immunocompromised or already have some kind of respiratory ailments. So the fact that along with the particulate matter that's in smoke, there are microorganisms that are not normally in the background air conditions suggests to us that there could be some impact on human health.
And with this type of research, can you tell where smoke comes from?
I love to think about smoke as having a genetic fingerprint.
Yeah.
And that genetic fingerprint would be associated with the source materials that are producing that smoke. So that is something that we're exploring too. The atmosphere is a very complex place.
Yes.
So everything is getting mixed up all the time. But we've been able, like I mentioned, to track some of the source materials and how they relate to the DNA in the smoke. And it seems like that relationship is pretty close. So we're thinking that potentially we can use that kind of indication, understanding the composition of smoke, as a way to understand what different sources of smoke are contributing to the smoke at a given location.
Thank you so much for joining us today as we look closer at the incredible research happening in the Gem State at our first R1 Carnegie Institute, University of Idaho. From healthcare to ecology, agriculture to aquaculture, and advancements in technology, U of I is addressing countless needs in our state and the world at large. To learn more about the incredible research happening here in the Gem State, simply go to go.uidaho.edu/Carnegie-R1. Again, thank you so much for celebrating this amazing achievement for the Gem State.